Okay, chapter 14 is the behavior of gases. So we will be learning more about gases. Yay! So 14-1, starting at section 1, we start off with properties of gases, which I suppose is important to know when learning about gases. So we have certain key concepts that we've been hitting, and it's that gases are easier to compress than solids or liquids, and that was a tester that we had to do. And so in this section, we will study the variables that affect the pressure of certain gases. So first, we start out with compressibility. And compressibility is a measure of how much the volume of matter decreases under pressure. So that has to affect with collisions and how that all works with gases. And then we move to the kinetic theory, which helps explain why gases are compressed more easily than liquids or solids. And gases are easily compressed because of the space between the particles in a gas. So if the particles would start to move faster, that means that everything would speed up and more collisions would occur. So then we go to the factors that affect gas pressure, and the amount of gas, volume, and temperature are certain factors that would affect the gas pressure. So then we learn about the amount of gas and how that affects everything, and the volume and how it goes into the temperature. And so in this section we just learn the certain different properties, I guess you could say, of volume and temperature, and how that relates in the cause-effect factor of gases. So moving on to section 2, it's the gas laws that we learned. And we learned that how pressure, volume, and temperature of a gas can be related. And we learned the combined gas law and how it is used to solve certain problems. So when we're connecting this to our world or trying to think how we can do this, think of a hot air balloon, and that it was designed to carry a passenger around the world. Because warm air is less dense than cooler air, the pilot heats the air inside the balloon to make the balloon rise. The pilot releases hot air through a vent at the top of a balloon to make the balloon descend. So when thinking about that, relate this back to our section and what we learned, and we studied that some laws can allow you to predict gas behavior under specific conditions, such as like this of a hot air balloon. So then we go to the Boyle's law, and that covers pressure and volume. And if the temperature is constant here, as the pressure of a gas increases, then that makes the volume, of course, then decrease. So Boyle's law states that for a given mass of gas at a constant temp, the volume of the gas varies inversely with how much pressure or how less pressure. So it all depends on your pressure and how the volume will be affected by that. So moving from Boyle's law to the Charlie's law covers temperature and volume here. So as the temperature of an enclosed gas increases, the volume increases if the pressure is constant. So as long as the pressure is constant, you'll have two increases for the volume and the temperature. Because then the Charlie's law, it states that the volume of a fixed mass of gas is directly proportional to its Kelvin temperature if the pressure is kept constant. So the main thing to remember about the Charlie's law is that the temp or the pressure has to be kept constant in order for this to work. Moving on, then we go to the Gay-Lussac's law over pressure and temperature, of course. And as the temperature of an enclosed gas increases, the pressure increases if the volume is constant. So in each of these, something has to stay constant, whether it's the pressure or the volume or whatever. Something has to stay constant. So this states that the pressure of a gas is directly proportional to the Kelvin temperature if the volume remains constant. So like I said, so long as something is remaining constant, you'll turn out with the right things that you're looking for. So then we go into the combined gas law, which describes the relationship among pressure, temperature, and volume of the enclosed gas. So just like this, the combined gas law allows you to do calculations for situations in which only the gas is constant. So then it showed us the right calculation to set it up when figuring out the combined gas law and when working with problems with that. So then moving on, we go to the section 3, which is the ideal gases. And in this section, we learned how real gases differ from the ideal gas on which the gas laws are based. So this is kind of a lot of back and forth, but we need to know everything before this to get us to the ideal gases. So the ideal gas law helps to calculate the number of moles of a contained gas requires an expression that contains the variable n. So then the combined gas law can be modified to include the number of moles. So this is helping us when we're working with moles and combining that. And then it leads us to the ideal gas constant and more of the ideal gas law. So then we get to the ideal gases and the real gases. And real gases differ, of course, from the ideal because gas at low temperatures and at high temperatures differ between the two. So that's mainly the main idea from that section, and just kind of keeps going in depth about those two things. So then we get to section 4, which is the mixtures and movements of certain gases. And in this section we found out about how or why the supply of oxygen is essential at higher altitudes, which that's pretty much a no-brainer, because if you were to climb a mountain, you would kind of need oxygen to reach the high altitudes. So this is how gases mix in with that. So, in a mixture of gases, the total pressure is the sum of a partial pressure of the gases. And it helps us by setting up an experiment to define this. And then it goes into telling us about Dalton's law of partial pressure. And it tells us that a constant volume and temperature, or the total pressure exerted by a mixture of gases, is equal to the sum of partial pressures of the component gases. So keeping that in mind when wanting to find the constant volume and temperature, that it's important. Then we have so many laws in these sections. We move on to Graham's law, and it shows us about diffusion and effusion and the differences. And gases at lower molar mass diffuse and effuse faster than gases of high molar mass, which makes sense. So he's just putting that into perspective for us. And then it goes on to more of the effusion and the effusion rate. And it's saying how you take the rate A over rate B, and that equals the square root of the molar mass B and molar mass A. And so that's kind of what this section's all over, are the key concepts of all the gases and how to work with gases. So that pretty much set us straight on gases.